Hello everyone, this is the second part 2 of the lecture on section 9.2, and we left off at this point right here. Okay, we're proving the fundamental theorem of finite abelian groups. Right, the fundamental theorem of finite abelian groups is if G is a finite abelian group, then G is isomorphic to a direct product of cyclic groups. And actually what you can say is a little bit more than that. Cyclic subgroups. Cyclic groups. And these may be cyclic subgroups of G. So it's a direct product of cyclic groups, but the cyclic groups may be thought of as subgroups of G. Okay, and we left off after part 1 at this point down here. All that's left is to prove that any finite abelian group G, where the order of G is p to the n, right, p is prime, is isomorphic to a direct sum of cyclic subgroups. Okay, and the proof for G with order of G equal p to the n is by induction on n. Okay, so like prime power order, like 2, 4, 8, 16, 32, 64, right, powers of 2, or 3, 9, 27, 81, 243, powers of 3. So groups of those orders. And that's all that was left after last time. You can check out part 1 for that. All right, the base case is when n is equal to 1 in p to the n. So here the order of G is p, a prime. And we proved in chapter 7 that groups of prime order are cyclic. So now the induction step. I assume that any G with, any abelian G with the order of G less than equal to p to the k less than or equal to p to the n is isomorphic to a direct sum of cyclic subgroups. Okay. Now say that G with the order of G equal to p to the n plus 1. Okay, if there is A in G such that order of A is p to the n plus 1, then G equals A, and we're done. Alright, so suppose that no element of G has order p to the n plus 1. Let A be an element of G such that the order of A is equal to p to the k is strictly, right, it's got to be a divisor of p to the n plus 1. And the only divisors of powers of a prime are smaller powers of that prime. Let A be in G such that the order A is p to the k, which is less than p to the n plus 1, is the largest possible order in G. Okay, for notational purposes, let H be equal to the cyclic subgroup generated by A. We're going to be talking about cosets of H, right? It's easier to write the coset HX rather than AX, right? This looks kind of sloppy, so we'll just let H equal A. So for notational purposes, let H equal the cyclic subgroup generated by A, and since G is abelian, H is a normal subgroup of G with the order of G mod H equal to P to the n plus 1 divided by P to the K equals P to the n plus 1 minus K, and K has got to be bigger than 1, bigger than or equal to 1, so that's strictly less than P to the n plus 1. Right, so G mod H satisfies the induction hypothesis. So by the induction hypothesis, G mod H is isomorphic to a direct sum of cyclic subgroups. In XL. Right, the elements of G mod H are cosets, so we're talking about cyclic subgroups of G mod H, which are generated by cosets. Okay, by the results of section 9.1, so by the result of section 9.1, the intersection of HXI, cyclic subgroup for HXI, and HXJ is just the identity element for I not equal to J. And the identity element in G mod H is H. And G mod H itself is equal to HX1 as a set product okay. G is HX1, the set product of these cyclic subgroups. Okay, so for any G in G, we now have that for any G in G, we have that the coset HG is equal to, right, a product of some elements from these cyclic subgroups. So it's HX1 to the E1, HX2 to the E2, HXL to the EL. So HG is equal to HX1 to the E1, HXL to the EL, like that. Or, X1 to the E1, X2 to the E2, XL to the EL. Right, so that's the operation in G mod H. So G itself, right, differs. So this element G differs from that by some element of H. Right, where H is a cyclic subgroup generated by A. So that's A to the E, X1 to the E1, X2 to the E2, XL to the EL, right, because H is just that. Right, so G itself is the product of the cyclic subgroups X1 to X generated by X1 to XL, along with the cyclic subgroup generated by A. Right? Every element of G is a product of power of A, power of X1, up to a power of XL. All right, so we would like to conclude that G is a cross X1 cross XL, not equal, but isomorphic to that. You would like that it's isomorphic to that, but it need not be because these guys might intersect. Okay? So G is a product of those guys. Okay, what we will do now, so to complete the proof, for each I, we will find yi such that hyi is equal to hxi in G mod H, and yi intersection yj will be equal to just 1 for each I not equal to j, and yi intersect a. Let's just be 1 as well. As things stand, the x's, so the x's, generate all of G. Right? Because the hxi's generate all of, where's that thing? Because the hxi's generate all of G mod H, where H is a cyclic subgroup generated by A, G is going to be a product of the xi's along with some power of A. Okay, but these guys might intersect. So as long as this holds, okay, and we get the additional condition that these y's only intersect in the identity, is those cyclic subgroups only intersect in the identity, then by section 9.1 we'd be done. Okay, by section 9.1, okay, we will then get that G will be isomorphic to the cyclic subgroup generated by A, direct sum with the cyclic subgroups generated by the y's. Okay, so all we need to do is find these y's, although this is kind of tricky, but we'll get through it here. So now consider just x equal to xi. Forget about the subscript because we don't need it anymore. Oh, I'm sorry. One more thing. As it now stands, xi intersect xj, right, is going to be a subgroup of H, which is a cyclic subgroup generated by A. So we need to find yi such that yi doesn't intersect H, except in the identity. And hyi equals hxi. Okay? So as it now stands, the A's, the X's, they only intersect in H. Because, hxi intersect hxj, right, was, as cosets, was just H itself. So the only possible intersection between the two is in H for xi and xj. All right. So for notational purposes, for notational purposes, write xi equal to just x. Forget about the subscript. We don't need it anymore. Okay, so just clutter up the picture. Okay, the order of hx in G mod h is, well, it divides the order of G mod h, right, which was equal to p to the something. What was it? N plus 1 minus k. Yeah, p to the n plus 1 minus k. So say that hx, the order is p to the r. So p to the r is the smallest positive integer such that x to the p to the r is an element of h, which is equal to the cyclic subgroup generated by A. Say that x to the p to the r is equal to a to the I, or I guess we shouldn't use I, a to the LMNOP, a to the q. Say that x to the pr is equal to a to the q, and write q equal to p to the, let me get my letters straight here, p to the s, t times p to the s, where GCD of t and p is 1. Right, if you take the prime factorization of q, well, there's so many factors of p, and then t has no factors of p. So you're factoring out all the p's out of q. Okay, I mean, there may not be any a priori, but there might be. So you just peel them off that way. Okay, so yeah, is a to the q, where q is equal to t p to the s. Now, the order of a to the t p to the s is the smallest integer, right? And it has to be smallest integer. It must be a power of p. Smallest integer p to the x, y, z, p to the z. Smallest integer p to the z such that a to the t, p to the s, p to the z, which is equal to a, t, p to the s plus z, right, because you got to multiply those guys, is equal to 1. Right, and because the order of a is equal to p to the k, that was our assumption at the beginning. We chose the order of a, so this order was p to the k, which was the largest possible order in G. Okay, because the order of a is p to the k, and the GCD of t and p is 1, it must be that the order of a to the t, p to the s is equal to p to the k minus s. Right, because we need that this is a multiple of k, p to the k. T to the p s plus z must be a multiple of p to the k. Well, again, there's no p's in t. T is relatively prime to p. So you just have to, throw in as many factors of p as you need, and that's k minus s, right? P to the k minus s. Okay. So now let y something else. So now the order of x in G. Right. So we looked at the order of hx. The order of hx was pr. So that was the smallest integer, such that x of that integer is a power of a. And we found that it was p to the r. So now the power of x, or the order of x, is p to the r. And now I have to take that to, some power up here so that I get 1. Okay, but that's just going to be the order of p to the, that's going to be the order of a, because this is a. Right, so it's going to be p to the r times the order of, not a to the tp, which is equal to p to the r, it's an r, not an n, times p to the k minus s, which is equal to p to the k plus r minus s, which is less than or equal to p to the k, right? Because the order of a equal to p to the k is largest possible in G. Okay? It's the largest possible order in G. So this has got to be less than or equal to that. Okay, well, p to this exponent is less than or equal to p to that exponent, as long as the exponents are less. Right, so canceling out the k's here, 0 is less than or equal to s minus r. So s minus r is non-negative. Now, let y be equal to x times a inverse p to the s minus r. Okay? So this y is going to be the guy that we're looking for. That's going to be the guy that we're looking for, so that y intersection a is going to be 1, yet it's going to be 1, yet hy coset subgroup, cyclic subgroup, was going to be equal to that. Right? So that's the thing that we're looking for, is to avoid intersecting the subgroup made by a, and then we're sticking that in there to do that. Okay, well, this is x, and that's in h, which is the cyclic, so there's just some crazy power of a right here. So this guy is an element of hx, of that coset. Right, so now we're going to show that the order of hy is equal to the order of hx, right? Then hy is going to be equal to, well, it's going to be a subgroup of the cyclic subgroup generated by h. It's going to be a subgroup of the cyclic subgroup generated of hy. Is going to be a subgroup of the cyclic subgroup generated by hs. But as long as the orders are the same, it's got to generate the whole thing. Right? So it's a cyclic subgroup of the same order as that cyclic subgroup. So it's got to be that cyclic subgroup. Right, so we want this to be true. And this was equal to what? It was p to the r, right? Okay. Well, y to the p to the r is equal to x a inverse to the p to the s minus r. All that to the p to the r. So that's x to the p to the r times a inverse. So, right, remember, we're distributing the exponent to both. Right, a, b to the c, and groups was a to the c, b to the c. in abelian groups, I'm sorry, in abelian groups, a b to the c is a to the c, b to the c. So I'm just doing that here, right? So it's x to that p to the r, and this thing to that p to the r. So I'm going to multiply p to the r by p to the s minus r, and that's just going to be p to the s, right? X to the p to the r, x to the p to the r, where is it? X to the p to the r was a to the q, where q is TPS. Right, so this is a to the t times p to the s times a inverse p to the s. So you add the, so that's equal to a t p to the s a to the minus p to the s. So now you add these two guys, right? P to the r. Right, so here we are. So this is a to the t, p to the s, a to the minus ps. So you add those and you get a to the t minus 1, p to the s, which is an element of the cyclic subgroup generated by a, which is equal to h. There can be no smaller exponent z such that y to the z, which is equal to x to the z, and then a to the a inverse to some big old exponent here. I'll just call it e, is in a, the cyclic subgroup generated by a. Let me rewrite that. Such that y to the z, which is going to be equal to x to the z, a inverse, I don't know, so what was it? Z, m, n, p, just q, just some crazy power of a, is an element of the cyclic subgroup generated by a because x to the z is not in a. Right? The smallest power of x that lands in the cyclic subgroup generated by a was p to the r. Was p to the r. That was the smallest power of y that lands in the cyclic subgroup generated by a is y to the, or x that lands in the cyclic subgroup generated by a was x to the p to the r. So this won't be in a, and that is in the cyclic subgroup generated by a. So the product can't be in the cyclic subgroup generated by a. Right? Thus, the order of y is equal to the order of hy is equal to p to the r, which is the order of hx. So that's what we wanted right from the beginning. Now, the order of y, right? Y, the order of y is not going to be, where is it? It's this guy. P to the r plus the order of this times the order of this guy right here, t minus 1 p to the s. A to the t minus 1 times p to the s. Okay, just a little error here. Y is equal to x a inverse to the p to the s minus r to the t p to the s minus r. That's what it is. Tp to the s minus r. So there's a t here, a t here, Tp to the s here, minus Tp to the s here. So now this product is a to the 0, which is equal to 1. That's what it was. So a to the tp to the tp to the s, a to the minus tp to the s, right? Tp to the s minus r, tp to the s minus r to the p to the r. So you multiply these, add the exponents, tp to the s. This is a to the tp to the s, the inverse, so that's 1. And there is no smaller z than p to the r, such that y to the z, which is x to the z, a to the power of q, is in q, because x to the z is not in a. Same thing as before. Thus, the order of hy is p to the r, right? Just like the order of hx. Now, also, since y to the p to the r is equal to 1 in G, and the order well, in G, we must have that the order of y is equal to p to the r in G. The order of y is p to the r in G, and as well, right? So the cyclic subgroup generates. So the first, as well as the order of hy is equal to p to the r. So the smallest exponent of y that intersects the subgroup generated by a is p to the r, but y to the p to the r is 1. So this intersection is just 1. Right? And that's that. So you fix the generators for G mod H, and then you get generators for G as well. All right, so I wanted to do an example, but I think the video is long enough for now. So as an example, I'd like to classify, well, maybe we can do it, all groups of order 8 up to isomorphism. So we've been talking about this for a long time, that there's 5 of them. 2 non-abelian, 3 abelian. The abelian ones, right, there's Z8, cyclic subgroup of order 8, right? But the other products of cyclic subgroups of order 8 are all the other. Oops, Z2, Z2. So this has order 8, this has order 4 times 2, which is 8. This has order 2 times 2 times 2, which is 8, right? And that's all the products of cyclic groups that whose orders multiply to 8. So that's all the abelian ones. Okay, so that's by the fundamental theorem of finite abelian groups. So now let's do non-abelian groups. So in a non-abelian group, G with order G equal to 8, there can be no element of order 8, because cyclic groups, because then G is cyclic and cyclic groups are abelian. Right? Furthermore, it cannot be that every non-identity element of G has order 2, because then, right, xy squared is equal to 1 is equal to x squared y squared for all x, y in G, which implies G is abelian, which is a contradiction. Right, that would be a contradiction. So you can't have that everything is order 2, nor can you have anything of order 8. So you have to have an element of order 4. So there is A in G such that the order of A is 4. Okay? You have to have that in a non-abelian group of order 8. So now take or consider G minus that cyclic subgroup generated by A, right? G minus 1A, A squared, A to the third. Right? Two things happen. Either there is B in G minus the cyclic subgroup generated by A with the order of B equal to 4, we'll call that case 1, or every element in every B in G minus A has order 2. Call that case 2. And, what are we expecting? We're expecting that, in this case, that you have the quaternion group, and then in this case, you have the symmetries of the square. Okay, that's what we know what the answer is supposed to be, but, we want to try to prove that, right? Okay. So let's do case 1. All right, so say, the order of A is equal to the order of B is equal to 4. Now, remember, the order of that product is equal to the order of the subgroup over the intersection. Right? Whenever you had subgroups A and B of G, the order of that product, that set product, was order A, order B, over order A intersection B. Right? All right, well, so that's what we get here, right, in this case. Because the index of A is 2, the cyclic subgroup generated by A is normal in G. So the subgroup generated by the products of A's and B's can't have order 4. It's got to be bigger than 4. Right? And then it's got to be less than or equal to 8. Well, it has to be a divisor of 8. It has to be 8, not A. Has to be a divisor of 8 that's bigger than 4. So it's got to be 8. Right? So 8 is equal to, this is 4 and 4. 4 times 4 over the order of the intersection. So that's 16 over the order of that intersection. So the order of the intersection is 2. Right. So it's a single element of order 2, so it must be that A squared is equal to B squared is the generator of A intersection B. A squared. Okay, so now we've got that. Now again, A is a normal subgroup of all of G. Right, so the coset BA is equal to the coset AB, so BA is A to some exponent, A to the T, B. It can't be that T is equal to 1. Because then G would be abelian. Because G is generated by A and B is not abelian. Right? So it can't be that BA is equal to AB, because then all powers of A and B would commute with each other, and all powers of A and B is all of G. So it can't be T equal to 1. Can it be T equal to 2? Can't have T equal to 2 because TA or BA equal to A squared B. A squared was B squared. Right, is equal to B to the third. Right, so BA is equal to B to the third. So A is equal to B squared, canceling the B's. But order of B squared is 2, and the order of A is equal to 4. So that's not good, right, either. All right, so it must be that BA is equal to A to the third B. All right, so G is the group generated by A and B such that the order of A is equal to the order of B is equal to 4, A squared is equal to B squared, and BA is A to the third B. But this is Q8. Q8 is generated by I and J, where the order of I is equal to the order of J is 4. I squared equals J squared is minus 1. And ji is minus k, which is equal to minus ij, because I times j is equal to k. I should go down the line and do this. Minus ij, but I is -1 is I squared. I to the third j. Right. So this group is the quaternion group of order 8. 45 minutes. Let's do the last one. Case 2. Every element of B and G minus the cyclic subgroup generated by A has order 2. Alright, so you got these other elements of order 2. So as before, A and B, right? So B is not part of the cyclic subgroup generated by A, right? So A is a normal subgroup. As before, the cyclic subgroup generated by A is a normal subgroup of G because it has index 2. And so this is a subgroup of G, which is bigger than A itself because B is not in the cyclic subgroup generated by A. But then it's got to be less than or equal to 8, right? So G equals 8. So A and B generate all of G. Okay? Since A is index 2 normal in G, B times A is A to the K, or A to the T, times B, where, right, can't have A to the TB for some T. 0 less than or equal to T, less than or equal to 3. Right, can't have T equal to 0, right, because then BA, because BA is not equal to B. Can't have T equal to 1, because G is not abelian. G, which is equal to A, B, is not abelian. Can't have T equal to 2, because BA equal to A squared B. What's the problem with that one? I'm going to get my notes somewhere. Because because BA equal to A squared B implies that BA to the third is equal to A to the, so 3 times 2 is 6 B, right, which is equal to A has order 4, A squared B. So BA is equal to BA to the third. So you cancel the B's. So 1 is equal to A squared with order of A equal to 4, contradiction. All right, so so t is equal to 3. So G is equal to the subgroup, this group generated by A and B, where the order of A is 4, the order of B is 2. There was no thing in there of order 4. And then BA is A to the third B. But we know this to be D8. Okay, so that's it. So that's all groups of order 8. Maybe we can do, so we know everything of order less than or equal to 12, all groups. Maybe we can do some more later on, but that's enough for today. Okay.